Okay, I guess we'll move on to the presentation. So we have four speakers tonight, four members that are going to do some short informal presentations. And we're going to start first with somebody that's online, Greg Shanos. Many of you may know Greg. Greg was a longtime member from back in the 1980s, and then he moved to Florida and forgot about us. Then during the pandemic, when we started doing our meetings online, he refound us and rejoined as a member. So he's going to talk to us tonight about the situation with Meade telescopes, right? Having gone out of business, Greg is an owner of Meade equipment, and many of you may be, and Skyscrapers is also one of those members. Some alternative sources for getting parts and pieces and service and support for Meade telescopes. So at this point, Greg, take it away.
Okay. All right, great. I'm happy to be here. Can y'all see my presentation?
Yes.
Yes. All right, great. All right, so this is my collection of Meade telescopes. And so now that Meade, Coronado, and Orion, they all kind of bought each other, are out of business. Many individuals that own these scopes may experience future issues with repairs and accessories. So that's what this presentation is all about, to familiarize everyone that owns the Meade Telescope Resources websites and individuals that are available for telescopic first aid and life support. And tribute to Meade. Meade really revolutionized two things. One was deep sky astrophotography. I remember in the late 90s, 1990s, they had the Deep Sky Imager, which is right here for $300. And it was the first that performed live stacking while in alt azimuth mode, and it actually undid field rotation. And then they introduced the advanced coma-free optical design, which they called the Ritchie Crichton, which it wasn't. But and then Celestron came up with their version, the HD. And since then, in that picture, I've purchased this Orion triplet Apo refractor, and I upgraded my H alpha scope to a Solamax 260 millimeter. That one's a 40 that you saw. So Meade accessories. So when they went out of business, there was an auction, and High Point Scientific purchased the entire lot of Meade, Orion, Coronado, and Orion products, and are selling them at their website for a substantial discount. And you could go to the website here and type in Meade, Orion, or Coronado, and once everything is sold, that's it. And unfortunately, most of the higher end items have been sold. They've sold all the Coronado H alpha scopes, a lot of the LX200 and other models, LX90s, they're all sold. So there's just the lesser accessories like finder scopes and things like that. But still check the website and see what's available. Scope Stuff also has another excellent resource for accessories for all manufacturers, and they have a wide variety of Meade accessories. So check out these two websites. And this is fantastic. There's third-party entrepreneurs that are developing their own versions. I know Skyscrapers has the LX200 Classic 14 and 16 inch, and Bob Napier also has, I think, a 14 or 16 inch too. So I highly recommend you purchase this. It's a improved hand controller, OLED display instead of the old LED display. It's only $169, so it's not bad at all. Okay, so it's a really good price, and this way you could have at least one, preferably two. So because those hand controllers tend to die, and if that dies, you can't really use the telescope. So it really behooves you to get that. And they also sell other things, encoders. There's a joystick that they made, and cables and kits. So check the website for details. I have the LX200 GPS. I don't have the Classic, but this looks very, very good. There's this website called Buttonworks that is for all types of mechanisms. Like you could get buttons to replace your remote for your TV and other things, but they have for the Meade AutoStar. So there's two things that they have that typically wear out on the AutoStar, and one of them is this little membrane wears out where you touch the keypad. So this will wear out, and what wears out even sooner is the LED screen here. Okay, so you can replace both of these. Now, if you have an AutoStar 2, which works on the LX200 GPS models like I have, you need to purchase this little diode, only 50 cents. And it shows you how to solder it in there. And so the LED diodes won't light up if you don't have this in there. So you got to get this. So even if you have the 497, just get it for 50 cents. It's not going to break a bank. And there's detailed instructions for installation. And another company that just came on is ScopeBits, and this took the AutoStar to another level. It's located in the UK, and and he calls it the Click Star, the Touch Star, and the App Star. And this replaces the AutoStar 2, 3, and also has a telescope bridge for Meade, Celestron, and Skywatcher. And then here's the Click Star here. See, it looks just like the AutoStar 2. And the thing is, it doesn't have the AutoStar 2 has these backlit in red, but these are white. They're not backlit, but that's okay, because given today's light pollution, you can see these anyway. So unfortunately, so they stand out pretty well. And there's also a joystick that comes with it. See it here on the side? And then what you can do is go up and down, and instead of using these little controls here, you can use the joystick to move it around. It's really, really impressive. But the only caveat is that it costs 220 British pounds and 16 to mail. So it was 236. But with the exchange rate, $1 is no, 1 British pound is $1.34, and possible tariffs, I paid 332.24, so I paid $96 more. Still well worth the price. And I have it here if you could see it. Let me see. Can you see it here? And it comes with its own little stand too. And then here's the joystick. It's really, really impressive. I'm really impressed with this. And it's updatable too. Okay, so that's really cool. And then, another cool thing is, once this is attached to your Meade telescope, you can attach it. There's a QR code, and with an Android, iPhone, or iPad, you can you can have it virtually on your cell phone. Isn't that incredible? And it looks just like this, nice and red, so it doesn't ruin your dark adapted vision. And then you can just touch it here on your cell phone and just leave this on the telescope, and you're good to go. It's really, really impressive. So that's a nice advancement there. And then ScopeBits also has what they call a telescope bridge, which here you can attach it, and this is only 80 British pounds. So it this will connect to an iPhone or iPad or even a computer, and you can attach it to a planetarium program such as Sky Safari or Stellarium, which is really, really cool. All right. So so this is really, really nice advanced stuff. And then another accessory too, which is similar to the scope bridge, is this here, which I just purchased, and this is from eBay. So uh, I'll have to experiment with this when it comes in. And then another great thing is a Star GPS. That now you can purchase this little unit here for 129, so you can add GPS to the LX200 Classic, which is really nice. Or And the other thing too is the Meade, the one that has the GPS automatically. They have a program here called Star Patch, which will update the GPS on the Meade LX200s. So that's really cool because it says copyright 2001, which in technology is 24 years now. So it's kind of dated, but this is kind of a nice thing. I gotta play around with this in the near future. Now, Meade repairs. Our very own skyscraper member, Tony Costanzo, has his own company called Astronomy Shop. And Tony resides in New Hampshire and is currently moving to Maine, but he also is a snowbird and he has a condo down in Punta Gorda, Florida, which is only a 45-minute drive one way for me. So when Tony's down in the wintertime, we get together, and Vice President Mike Corvese comes down too and spends some time with Tony. So we all get together in Florida. So that's kind of neat. But Tony can repair all these scopes. He also repairs Orion, Questar, Takahashi, Celestron, Unistellar, the old Unitron refractors. And he just told me he took apart a Sea Star. So now he's working on that. So soon he'll be able to fix Sea Stars. And then there's another person who repairs too, Gary Engel from Maryland. And no, where is it here? And he can also repair it too. So he does a lot of the Meades and also upgrades too. And Tony highly recommends him too. So you can either have Astronomy Shop or Meade Mods to repair your telescope. So contact each individual regarding the issue and a quote for repair. And then in conclusion, most products are well manufactured and should last a lifetime given standard working conditions. So for all meat aficionados, since the company's out of business, which really kills me, don't despair since there are still resources out there for accessories and repairs. And this presentation has familiarized you with these different companies and manufacturers and also repairs are from Astronomy Shop and Meade Mods. And if all else fails and you can't repair it, you can always defork the tube and attach it to an Ioptron, Skywatcher, Losmandy, etc. Any go-to Altaz or equatorial mount that's on the market that will hold a 8, 10, 12, 14-inch Meade, and then they come with their own hand controllers and just use that. So in the future, unfortunately, 10, 20, 30 years down the road, this will probably be your only option because parts and repair will pretty much become non-existent. So definitely buy some of these hand controllers, either from Clearline or from Scope Bits, because these companies won't be in business forever, and they've really upgraded it. And the hand controller really does all the calculations. So it's a real godsend that these companies, people really still care about Meade and are out there, making accessories and upgrades and repairs. So that's it. Thank you. Any questions? 13:30.
Any questions for Greg? Just as an informal polling, how many people have Meade equipment here? All right.
Yeah.
Okay, good. Several people.
How many? Can you raise your hands again? Let me see. Yeah, so quite a few. Yeah. So were you all familiar with these websites? Probably not, right?
Yeah, I've seen them.
Oh, you have. Okay.
Yep.
So, and I have the hyperlinks on the presentation, so you can go right to it, or just Google it, Clearline Technology, Scope Bits.
Hey, Craig, on the repair resources, did you meet, was that Gary Hand?
It's Gary Engel.
Gary Engel, okay.
Yeah.
Difference.
Yeah, right. Okay. All right. Any other questions for Greg? All right, well, thank you, Greg.
All right. You're welcome. Thank you.
Okay, so next up, we have a more recent member who's joined our organization. We have Michael Kerr, who is going to come up and talk to us a little bit about Auroras. And if you could give us a little bit of an introduction, since most people don't know you. Come on over here.
Yeah. My name is Mike Kerr. I'm a new member. Well, about a year. I came to one observing session and then got really busy with work and life and didn't make it to any meetings until the AGM just a few months ago. And I'm starting to get to meet people and I'm being trained on the Clark, which I'm really excited about. My background, well, I'm a physicist, working physicist, and I have a degrees in astrophysics. Done a little bit of astronomy in my life, mostly physics and applied physics. The bulk of my career was at MIT Lincoln Laboratory up in Lexington. And then right now I teach part-time physics and astronomy at Eastern Connecticut State University. So that's my background. A little background and context on this talk. We give regular public planetarium presentations and shows at Eastern. We have a nice 40-foot dome, 65 seat auditorium. And I gave this talk on the Aurora back in March of this year. Well, something like this. It was based on this as the background to this. You don't often see the Aurora talked about in astronomy circles, even though it's relevant for sure. So the time was right because according to who you talked to, we either went through solar maximum last fall or we were going into it during the spring. And I'm frankly a little bit out of touch where we really are, but we're somewhere near solar maximum. So we're more likely to see auroral displays during the next several months to a year or more. And so I thought that was the relevant topic. And so we brought that forward to the public at that time. It was a public presentation for the general public, not quite as a knowledgeable audience as we have here. So this talk is going to be kept at that same general level, if that's okay. Now, that's the background and context. I have also a couple of disclaimers. One is that I haven't done auroral research since I first came out of school. It was the first thing I did, and you'll see a little reference to that in this talk, as a surrogate to nuclear weapons effects, believe it or not. And so early on, I had done that sort of research, high altitude atmospheric physics, high energy deposition in the atmosphere, and that sort of thing. But that's a long time ago. So if there are any questions, don't make them detailed because I probably won't know the answers. The other disclaimer is that I'm just going to, this was a public presentation with lots of nice pictures. So I borrowed profusely wherever I could to put this together on short notice. And I was really fortunate right in the beginning of March that Sky and Telescope had just run an article by a fellow named Bob King with some beautiful photographs and on the Aurora, and he had done some Aurora chasing in Norway. So the timing was good. I freely borrowed his material and I have it here tonight. So I want to acknowledge Bob King and the good people at Sky and Telescope magazine. So that's the long-winded intro. Blood Rain, Candle Dragons, and Merry Dancers. Obviously, I'm referring to the Aurora. Those are some of the terms down through the ages about the Aurora. A little poetry from the midnight lands comes up the dawn. Lo, a cold flame has covered us. Lo, in the nighttime, day has come upon earth. If you've ever seen a big and beautiful auroral display, it can be absolutely stunning and amazing. I grew up under very dark skies in the northwestern corner of the Adirondacks, and I saw a lot of auroras growing up. In fact, it's one of the principal reasons I went into physics in the first place, was having been inspired by scenes not quite like this, but some very dramatic scenes for sure. This poem was by Mikhail Lomonosov, a Russian poet from the 18th century, also a scientist. He discovered the atmosphere of Venus, and he discovered the concept and principle of conservation of mass in chemical reactions, but with a poet's heart. And it's hard not to become poetic when you see the aurora. At Eastern, we just did last semester or last year, a whole year, the whole campus-wide initiative, a reading initiative with a particular book called The Bear, a post-apocalyptic novel set on the hills and slopes of Mount Monadnock in New Hampshire in the future. And there's a quote here by the main character that she had stepped outside of a little cave in the middle of the winter, and there was a quarter moon had long set in the west, and to the north shone these lights of green and yellow and red that shimmered and waved like water across the upper air of the horizon. She gazed in wonder at the lights and what could be alive there that high in the sky, and she took strength from that. If you've ever seen an active auroral display, the term alive fits very well. And of course, now we know the phenomenology behind this. So we have blues and greens and reds that were referenced by the character, and we know the wavelengths of these, and we know the causes of them. Molecular and ionized nitrogen at some lower altitudes and atomic oxygen and so forth. And then when you get to the yellows and pinks that were referenced, it's the mixture of these different colors that are on display during the aurora. So what is the aurora? Well, according to the Cambridge Dictionary, it's just that natural appearance of colored light in the sky. Very simple, very experiential. It's usually seen in the latitudes nearest the Arctic or Antarctic, and that gives us the aurora australis and aurora borealis. And these are sample pictures there. This is from Bob King's article, very dramatic. And you can get some extremely dramatic and unusual shapes in these displays. Look at that shot there. It almost looks like an X-ray of someone's hand. Just amazing. So the modern term, was thought to have been coined by Galileo in the 17th century. Aurora, the Roman goddess for the dawn, and Boreas, the Greek god of the north wind. And then Auster for Australis is the Roman god of the south wind. But cultures all around the world in the high latitudes have experienced auroras, and they've come up with their own names. And so just quickly, we have Candle Dragon, Ball Player, Dance of the Dead, Sky Dwellers, I'm just picking at random, Battle Lines of Fire, Bloody Armies, and then from my own cultural heritage, the Scottish Highlanders, it's the Merry Dancers in the sky. Among the Iglulik, a powerful helping spirit. Whistle for it and it crackles and comes nearer. Spit at it and it runs together and changes shape. Some people hear the aurora. The last I knew, and my information's stale, it's about 25 years old, people were still investigating whether or not there are sounds associated with the aurora. And they were enlisting the help of the ordinary public and citizen scientists in order to sort of track that down. I know my father heard the aurora. I've never heard the aurora, but he talked about whistling and crackling, just like the igloo. The Labrador Eskimo, light from torches shining through a hole in the sky, that whistling and crackling noise of voices of spirits trying to communicate with us, but you always have to answer it with a whisper. A little sinister overtones there. And Nunavik, spirits of walrus playing a game with a human skull, ball game. Among the Yupik and Yupiat, spirits playing ball with the heads of disobedient children. The Menominee, Midwest, torches of friendly giants to help spear fish at night. And the Northern Adirondacks, I've speared fish at night with cousins under the aurora. It's an amazing experience. Among the Fox people, in the gathering of ghosts of slain enemies, eager for revenge. And this isn't advancing quite as quickly as I thought. The Ottawa, a great fire lit by the crater to indicate interest in our welfare. It's funny, I'm used to looking at the screen. I'm going to look at my screen here. I can read it better. Among the Russian lamps, battle spirits between spirits of those who have been murdered, and so forth. You get the idea. Ancient stories associated with this. Among the Norwegians, at least some Norwegians, reflections of schools of herring, far off oceans. It makes sense, an ocean-going people. Among the Greenland Vikings, where Greenland was considered the northern edge of the world, it's a fire encircling the ocean, and some of that firelight is seen on the horizon. That picture on the upper left is not a watercolor drawing, that's an actual photograph. And among some of the Finns, the aurora is seen as having been created by this fox, Renku, as he splashes snow into the air with his tail. So we experience the aurora. People have experienced this down through the ages. The Middle Ages in Europe, 1500s, you can see the sky all the way across, and maybe in slideshow mode. Medieval Europe, the sky on fire, people pointing to the sky and trying to put together the pieces of the puzzle and figure out what all of this is. Arctic explorers and people who opened up the Northwest Territories and travelers across the northern latitudes of Scandinavia. So you can see these here. In the Arctic in the bottom right, there's a high rigged mast ship off in the distance. An Alaskan fur trading post and a settler's notebook that says that this is a sky snake that's wiggling its way through the sky. Fridtjof Nansen, a polar explorer. You can see this here. And this isn't just fanciful woodcut or pen and ink drawings. Here's a photograph of something very similar and spectacular. Likewise, Alaska, 1885, some explorers sketch notebook, and then a more modern photograph, something very similar. Really exciting stuff. Photographing the aurora. This is the oldest known photograph of the aurora from 1892. We can still do that, even with something as simple as a cell phone. Back last fall, or 2 falls ago, last fall, in Connecticut, we had a pretty good energetic display, red. My colleague, senior professor in our department, Zoran Meade, took these pictures with his cell phone on the left, and I took this one on the right. Bob King had in his article, The Sky and Telescope, his trip to Norway. You could see the aurora outside of the airplane. I used to fly to Europe a lot, to Brussels for work, once a month at least, and I always sat on the left-hand side of the plane going over and the right-hand side coming back because I wanted to see aurora over Iceland and over the polar regions. And I often did. It was worth the window seat. If you had the opportunity back in the day and you rode the space shuttle, you might see it from low Earth orbit like that. Richard Sanderson, president of the Springfield Stars Club. You probably know Richard. He took this picture of the same auroral event last fall in his backyard in Westfield. So what is the aurora anyway? Well, we have to start with the sun. I think you all know this, of course. The sun, Sol, it's a giant ball of plasma, a very big hot ball of gas. It's a massive centerpiece of the solar system. It is the solar system after all. But it's a distant neighbor. It's our nearest neighbor. We can get our first and only up close and personal look at a star by looking at the sun. But it's a distant neighbor, 92 million miles away on average, roughly. And I call it the world's greatest influencer because it is the dominant effector in the solar system itself. And everything here on Earth is influenced by the sun. And I want you to get a notice, just sort of get this picture in your mind. This is the heliosphere. So here's the sun and the solar system at the center, and we have the streaming out of the solar wind and the particles as they go off into interstellar space, and they impinge upon the interstellar wind, which is a collection of high energy particles and high energy particles from all the other stars in the galaxy, and we're streaming off as a system to the upper left along the solar apex, along that red arrow. And you can think of this like an egg almost, or like a cocoon. There's this termination shock where the solar wind of the sun slows to subsonic speeds in its own environment. And then there's the heliopause way out here where it's sort of the edge of the influence of the solar wind, but it's plowing through deep space, and it creates a bow shock, just like the front of a boat creates the bow wave as it moves through water. And it's deflecting a lot of that high energy material around the solar system and away from the Earth, but not all of it. And of course, it is the near Earth space environment, which is a very thin and fragile shell around the Earth where all of this auroral activity takes place. And so we have to look at it a couple of ways. There's the aurora itself, but there's also the study of the high altitude physics and chemistry of the Earth's atmosphere. And we call that aeronomy. And one of the phenomena of aeronomy is the so-called air glow. It's a non-thermal radiation that's emitted by our atmosphere and other planetary atmosphere. Non-thermal means it's not in equilibrium. There's a driving function, a force of these higher energy particles coming in. Our atmosphere reacts like a living organism, and it's not in equilibrium. And this is happening all the time, 24 hours a day in our atmosphere. And there's a dramatic change from night to day to night along the terminator, that dark and light shadow of the sun on the Earth. all studied under the rubric of astronomy. And so you see air glow here. There's a picture from orbit, and it's an awful lot like an aurora, but it's not quite the same. And this is taken from the space shuttle or the ISS. I don't remember which. I took this right off of Wikipedia. But look at the lightning storms up here on the right as it goops. You can see, but you can see that air glow. The atmosphere is alive with activity, emitting light. There's a lot of chemistry going on there, photochemistry. So I'm moving on because I'm conscious of time. Our magnetic Earth. This is the source of all of this, and I think you all know this. Of course, the Earth is magnetized, and we have a spinning core, and our magnetic pole wanders around the northern and southern polar regions. It's not aligned with the spin axis of the Earth, but it wanders. But there is that north and south pole, and so like the other cocoon picture, this is a cocoon picture of our Earth moving in its orbit around the sun in the solar system with the solar wind we're bathed in the solar atmosphere, the outer atmosphere of the sun. And as we stream through, our magnetic field creates this shield and this cocoon around the Earth and deflects most of that high energy radiation away from the Earth. But once in a while, these lines begin to reconnect because the magnetic properties and electromagnetic properties of that plasma that's coming off the sun is very active, and it's very dynamic. And so once in a while, it'll recombine, reconnect, and short circuit and throw lots and lots of particles right towards the Earth from the backside generally. And they stream towards both poles, spiral in at very high velocity, impinge on the molecules and atoms in the upper atmosphere, and give us the light of the aurora. And so to put it in perspective, here's Mount Everest here on the bottom right, and we have the auroral phenomena from about 100 kilometers up. Generally, you think of 100 kilometers as the upper edge of that very thin atmosphere of ours, but there's still trace elements above that. And so about 60 miles and up is where the aurora occurs. So we can sample that atmosphere. An early project I was involved on, I did all the theoretical predictions of what this balloon-borne project would see. This was in support of the Defense Nuclear Agency and Air Force Geophysics Lab. And my colleagues built this balloon platform and launched it up to 70 kilometers, taking laser measurements of temperature and wind and pressure and all of the atmospheric constituents so that we can anchor our theoretical understanding of what was happening with the aurora. So auroral chemistry, we have radiative recombination at the top. You have a certain element combined with an electron that's coming in from the sun. There's free electrons everywhere, and it gives off this H nu, the Greek letter nu. That's a photon of light, and so forth. It involves individual atoms. It involves collisions among molecules and molecules themselves. Very complex, but it gives us these beautiful forms. And so you see this quiescent sort of a curtain shape at top, and then as you go down, there's more and more energetic phenomena, more activity, and we get these active curtains with rays, and then the pleated curtains, and eventually the swirls and the holes that are just spectacular to see. It creates the so-called auroral oval. Sorry, I'm tongue-tied tonight. This is in 2005 over the southern pole, and you can see that auroral oval. This is characteristic of the aurora. 65 to 75 degrees latitude, north and south, and about 60 miles up, and so forth. And not just our planet. Here's Saturn, and you can see the auroral oval there on Saturn, which immediately tells us that Saturn has a magnetic field. The aurora itself, this is we're kind of in a quiet period right now. If you look at this histogram on the left, it's the 12 months of the year. There's a peak, those two purple peaks, around the equinoxes for auroras. And we're near solar maximum. We expect to see auroras over the next few years, and keep your eye out around the next equinox in September, because there's an enhancement effect by two causes that we think. One is the so-called Russell-Farad effect, which is the Earth has a magnetic field, and the Z component of the magnetic field, it exists in three-dimensional space. Well, so does the sun. And twice a year, those two fields happen to be anti-aligned, and that enhances the chances for auroras and the intensity of auroras. And the other thing is twice a day during the equinoxes, the the Earth's magnetic field is aligned perpendicular to that solar wind, which also enhances the auroral effect. So keep your eye out September and look for the forecasts. I guess I won't get there yet. The sun, our active star, really briefly. This is a cartoon depiction. You all know the 11-year cycle of the sun. We go through minimum and maximum, generally, not always. And then the sun is a plasma. It's a hot gas. The surface is all ionized. And so we have free electrons, and it's all of its magnetic properties and electromagnetic properties get tangled up in that gas, and you get nodding and other things that happen in the magnetic field. That tends to spew off material, sometimes episodically and catastrophically, and those lead to solar storms and space weather and so forth. We're obviously watching the sun very closely, and that allows us then to forecast what we can expect for solar weather and auroral activity. There's a good auroral app that I have on my phone, and I check it periodically to let my students know if there's a good chance for an aurora. This upcoming week, pretty low. If it's called My Auroral Forecast, if you ever want to find it. And we look for KP indexes up in 6 or 7, 7 or 8 or 9 were really good prospects for auroras. Can't always predict. And so what do you do? What's the next best thing you do? This is early research that I did. That small company I worked for called Visidine used to send people up to Poker Flat, Alaska, and they would wait for an aurora. And when the aurora, they wait up all night. And when the aurora would happen, they would launch a small sounding rocket into the aurora to sample the aurora itself. Well, you can't sit around all the time. That's expensive to do. And so we created our own aurora, an artificial aurora. And we set up a Terra Malamute rocket, and it separated into what was called a mother and daughter payload. And the mother payload had a sensor on board, and the daughter payload fired a high energy particle beam into the upper atmosphere to create an artificial aurora, and then observed by the mother module. And my work was to predict what that instrument would see. And it was done as a surrogate because back in 1963, the US and the Soviets and every other nuclear nation agreed to a non-atmospheric test ban. There was a test ban treaty for nuclear weapons. And so there were gaps in the data up until 1963. They would set off nuclear detonations in high altitude environments, and they would observe them with sensors, but there was a dearth of data for the infrared. And so one of the ways to gather that data was to create artificial auroras and use natural auroras as a surrogate for those data. So that was the motivation behind that research. If you can't do it that way, do it in the laboratory. And so way back in 1911, in Oslo, one of the pioneers of auroral research created this instrument. He called it a Terrella in the laboratory, and it created with the gases surrounding this ball with the magnetic poles on it, and he could vary all the parameters and create artificial aurora and begin to study it right in the laboratory. And since we now know that auroras occur not just on Earth but on other planets, the term is morphed into Planeterella. And I'm trying to convince our department to build one of these for our lobby for our planetarium. It might be a nice thing for this room as well. That's my presentation. One more quote from Bob King, a quote from Bob King in that article. He says that the majesty of nature manifests itself in countless big and small ways, but in our daily hurry, it's sometimes easy to miss the small ones, but not the aurora. It knocks you on the head. It makes it impossible to walk away untouched. And I would agree with that. So thank you very much. I hope I didn't go over, Michael.
Okay, so I wanted to talk to you tonight a little bit about the Sky Kids observing program. It's something we've been doing for the last 2 years with some younger children. And I wanted to just take a step back and just give you a little bit of background on how we got here. So if 2 years ago, we put together a subcommittee, right, to talk about youth programs from more of a strategic level. Right, and so the members of that team was myself, Francine Jackson, Dave Eustace, and Mark Casey. And we spent a good couple of months, right? Kind of going through saying, what are we looking for? What kind of programs, do we want to have? Where would we put them together? So kind of, fleshing out the whole thing, try to do it in more of an organized manner. And, instead of me going through, all of that, this was kind of the result we came up with, is that, there were 4 important strategic things that we needed to have in order to run a good youth program. One was to have a curricula, right? Have a solid curricula, right? That was informative, that was adaptable, to cover many age groups. The second was volunteers. This was the most important, right? The program was never going to get off the ground without any volunteers.
You're bouncing off the wall and there's an echo.
Because I'm too loud. I actually don't need a microphone.
No,
I've got a
no,
PA built
don't
into my
need-
chest. So, so my mother used to say, she said, Mike, you're feeding back and turn it down. Is that better like that? That better? Yeah. They should have moved the mic away a little bit because I tend to speak loudly anyway. No one's ever telling me to speak up. I can tell you that much. So I mentioned the curricula, volunteers, and then we talked about the channel and how would we deliver this? Would we do it here? Would we have a central location? Would we do it locally? And then about promotion. How do we get the word out? How do we let people know that we're doing this? Right? So what we did in our first year, we actually went with what's called the Sky Puppies program, okay? which is a program offered by the Astronomical League. Right? And so we thought we had this kind of ready-made kit, right? And so they did have some nice information that they sent to us, and essentially they had a list of criteria and say the kids need to do these 10 things, right, that were on the list, but unfortunately there wasn't any how yet. How do you do this? How do you get the kids there? So we kind of had to write that program as we went along. Right? And what we found is, as we were doing this, is that some of the criteria that they had listed, this was way beyond what a 6-year-old. Because let me back up. The Sky Puppies program was designed for kids 6 to 10 years old. Okay, and just as an example, one of the requirements was that the child was required to find 5 deep sky objects with a pair of binoculars. I can't see a 6-year-old doing that. Never mind a 10-year-old trying to do that, right? Trying to find 5 deep sky objects. But so as we went through this, we kind of worked with that, and there were some others. That was just one example. There were some other things that just seemed to be too rigid for the type of program, for this age children. So when we came to the next year, that was the Sky Puppies, right? And then the next year we decided we changed the name. So we weren't going to use the Sky Puppies program anymore, but we kind of went similar to what they were doing in the Sky Puppies. We kind of relaxed the requirements, so we didn't have these these tasks that were impossible for small children to do. So we called it Sky Kids, right? And what we did, we began a partnership. Our specific example is we did it with Portsmouth Public Library. We opened up the age group instead of 6 to 10. We called it 6 to 11, but we even allowed. This past year we had a couple of 5-year-olds, because what you do is you get siblings, right? You get a 7-year-old that comes, and the parents are there anyway, so they bring in the 5-year-old. So and we let them. We even had kids as old as 13 or 14 in the first year, right? That we let them in. And again, under Sky Puppies, not allowed. They had to be between 6 and 10, or they weren't eligible to get a certificate of a pin or a pin. But what we did was came up with our own pins and certificates for the kids that were outside that, right, in the first year, right? So the second year we did go with the Sky Puppies, and we did this, right? So we ran the program twice a month, so it wasn't a big load. We went from October to April, right? And we did it twice a month, right? We kind of worked through that schedule, so it wasn't too bad. It wasn't like it's something you had to do every week. It was kind of every other week, and we had things with the kids. And we had the curriculum that we had written the year before, and we actually added to that because we actually went another couple of sessions longer. And what we would do is, if we had clear nights that fell on the nights that we were having the class, we would bring telescopes and we would go outside. And so the things we were doing in the class, we would take them outside and show them. Okay. And so what we mostly did with the children is we focused mostly on constellations and we focused on the solar system, right? So we had a set of constellations that we would go through. We would actually do like a 10 or 15-minute story time, right? Where we would do an adaptation from Greek mythology, right? And give them a story about that particular constellation. And it's amazing how much that helped them to retain the information. Because you'd bring something up weeks later and they would remember that constellation because of the story you told them, right? So that would be kind of a weekly thing we would have. And then we would bring in other concepts, right? We did a lot with with the moon, with the sun, with the solar system. We did a little bit on deep sky objects. We kind of gave them a variety of things. And anytime there was something in the news, we would put that in there. If it was a comet, or when T Corona Borealis was supposed to, kind of light off, we kind of talked about that with them, right? To keep an eye. So we would bring in the current, the current events as well. This just kind of describes what I was talking about. We do provide them with materials, sketchbooks, observation sheets, because we actually ask them to use the observation sheets when they go out. So we give them homework, and it's basically their homework is to go out and look at the sky, right? And another part of it, we also actually ask them to do research. We give them a list of robotic missions and ask them to do a little bit of research and then come back and share with the group. We're not asking them to do a book report or anything like that. Just look it up, have your parents help you, and then come in and tell the rest of the class about what that mission was. When it launched, what it was supposed to do, what the results were. And if we get to basically a 2-minute thing, for the kids, but it makes them feel important. They went and looked this up, and they have the information to share. And like I said, we did use the telescopes when we had. So our curriculum had to be flexible. Because we would have a plan for a certain night, but then we knew the sky was going to be clear. It's like, okay, we're going to bring telescopes out, right? And so we'll move that night to a different night. And unfortunately, with the weather here, I know the first year I think we got out 2 nights. Last year we did this, we only got out 1 night, right? But we were actually able to get out that wasn't that we were able to see. This was our class from from this past year. So we had 13 kids. And again, we did this one as Sky Kids, which was completely a Skyscrapers production. So we had certificates from Skyscrapers, and we gave them we bought the NASA meatball pins, right? And they each got a pin, and they each got a certificate for the for the work that they did. And it's amazing because the rules at this library was that the parents had to be present, right? And I guess the library has that policy for anything because they don't want kids running around in the library. So they required the parents to be there. We got so much engagement from the parents. The parents would ask as many questions as the kids did, right? So you also got this like education of the parents as well. And they would be there when we were going out at night, and they were, looking through the telescope. Oh, wow, that's cool. And they were asking all kinds of questions. So you kind of had we had a bigger group. When you look at, we had 13 kids, then you'd have 1 or 2 parents with each kid. We got a pretty sizable group that were there in the in the hall, and then out doing observing. So I personally find this very rewarding. I got that science spark when I was a young child, right? Because I had a very good 5th grade teacher that lit that, and I knew from then on I was going to be in the sciences, right? And I kind of enjoy putting this information out so that maybe I light that spark in some other child, right? And it's amazing some of the sophisticated questions you get from a 6 or a 7-year-old, right? Because they've got access to so much information now on the on the internet, and they have some very sophisticated questions at times. So it's it is quite amazing. So again, I wanted to tell you about the program, but I also wanted to pitch the program a little bit. Say, listen, if anybody wants to do this, right, this is the time to be to do the planning, okay? And Mark Casey and I would recommend, if you were going to do it, find somebody to do it with. 2 people was perfect, right? Because you didn't have to speak the whole time during the class, and you could kind of, when you're doing activities, because we always did a lot of hands-on activities with the kids, because again, you can't get in front of a group of 6-year-olds and lecture for an hour, right? So we had story time, we had activities, things that they were either drawing or they were building or making, or things that were kind of, Q&A, bouncing around the room. We always had some kind of activity, right, to keep them engaged, right? Because you could tell if you were losing them, right? If you had one too many slides, you were starting to lose them. But so I would recommend 2 people, because just to handle a group of 13 kids or 15. The first year we had 15. This last year we had 13. If you're interested, let me know. We've got everything. We've got like tons of material now. We've got a curriculum written out, class by class. We've got all the materials that we've got from the internet. We could fill up a thumb drive, with all the stuff to help anybody do that. And I'd even be willing to help out with the assistance. We weren't sure what we were doing the first time, but what I did was I approached the library. The library loved it, right? Especially when I told them it didn't cost them anything, right? They were like, because they love to have they love to have programs, right? And so they were a great advertiser for us. They advertised in the library. They advertised on the website. They gave us the any copies we needed for for handouts for the kids. They would make all the copies for us. So they were really helpful in that. And then what I did was I reached out in our town. I reached out to the principals of 2 elementary schools and, sent them emails, explained what we were doing. They loved it. They're like, oh, this is great. We're going to put this in our newsletter. So, we also did some other advertising. We did posting on Facebook. We did stuff in the newspaper. But I'll tell you, the local newspaper. But I'll tell you, I polled, with the first group and the second group, everybody who heard about the class was either through the library or it was through the school. That was it, right? Nobody responded to the newspaper. Nobody responded to Facebook or our website, because it was very local, right? But it was all going through. So, team up with the local schools. That's what the first year we did, the 2 public schools. Second year, we added, there were also 2 private schools in town. We added them. One, I got no response from. The second, I got a response saying they wanted us to do one just for them. It's like, oh, sorry, right? But we did get the public school engagement, right? Which was, two big elementary schools. So if anybody's interested, contact me. Like I said, now's the time to do that planning, because you getting ready for because we started it in October. We waited for the kind of the September, everybody's just getting back to school and kind of getting in the routine. We did we held an information night, I think, sometime in September for the parents to come and hear about the program. We did it at the library. We did an information night, and we did signups that night. That's basically where we got everybody signed up, and then we started at the beginning of October. And again, every 2 weeks, that was kind of our cadence. And again, if you like doing that and you like working with kids, this was a lot of fun. I really enjoyed it. At the end of the program, we had an awards night where we gave them certificates and the pins, and we had a cake and juice, and the kids just loved it. The parents loved it. The library loved it. We loved it. It was just a great fun fest for everybody, right? So if you're interested in doing that kind of thing, let me know. I'll be more than happy to help you to get it started, in your town. And like I said, I recommend going with the local library. That's what we did, and they were, they give you a place, they give you resources, they give you advertisement, right? And they love having that. But if you know any other organizations in your town that that would be as helpful in that works too. So I'm going to leave it there. And like I said, if anybody can contact me, I'll probably run an information session maybe in the next month or so that I'll advertise, through the club, that if anybody wants to come on, and I'll go through the program in a little more detail and take questions from people on, what are the kind of the things that we faced and what we came up against. Steve?
Yeah, has there been any discussion about working with club scout?
We haven't.
I know you haven't, but I'm curious around the country whether that is another venue to do this.
Well, they do. I know. I've done some work with the Girl Scouts, and the Girl Scouts do have a Space Explorer program, and so I've done some work with the Situate Girl Scouts here. It's not anything that we've kind of advertised on because you need another set of volunteers, and you need an organization if you were going to kind of bring that out into more of a public venue.
That as another venue by which we gather up a bunch of children.
Absolutely. Like I said, we did this one, we only did this one program because we only had myself and Mark were the only ones that followed. We did an information session. We had several other skyscrapers came to the meeting. They were interested, but they weren't really ready to commit, to doing the program. So we did have some interest, but when it came down to actually executing the program, it was just, Mark and I, right? And I'll tell you, you wouldn't want to run more than one of these. I mean, having one was not a heavy lift, but if you were doing 2 or 3, that it starts to become a job, right? If you were doing that many. So yeah, if we had more people to do it, bringing a program out to the Girl Scouts and the Boy Scouts would be fantastic. And we did have that. Remember, Francine, we did have that in the strategic plan. Is looking at the scouting, right? And we even had some tiering of age groups as well, getting into like junior high and again, you need volunteers, you need people to be able to do that. Kathy?
And some little troops of, I don't know how old they were. Yeah, I think the difference is that people will come to you out of interest. If you just have a bunch of Boy Scouts or Girl Scouts, they are grumpy, and they may or may not have a certain amount of seriousness about even their parents. Because we found that the parents weren't very well informed about the things we were talking about, and it could get off off in a direction you don't want to go in very quickly if people don't have sort of a they said, I elected to be here based on, or they're having a program, let's go see what it's like, that kind of thing.
Right.
So having people select you and want to be part of something long term, I think is an important commitment. I'm not part of the family, and that makes a big difference. The family is going to make that a more.
Yeah, absolutely, because I mean, these children their parents have to bring them right to these classes, and we did get very good attendance. I mean, yeah, children missed a class here or there, but for the most part, we had it was very well attended. And like I said, I think once we got into it, the parents were very interested. They liked coming to it. I mean, I overheard 2 parents talking while we were taking a break, and they said, "Oh, this is really cool. I never knew all these constellations. I could go out and name Orion and this and that." She's talking about all the constellations she could name in the sky. So we were having this effect of teaching the children, and the adults were getting something out of it as well. All right, I don't want to talk too much further. Any other questions?
Just another homeschool communities, that might be a source for kids that are really probably would like to participate.
We actually had that in our strategic plan as well, right? And again, we'd love to be able to reach out to all of these different groups, but we need a bigger organization, more infrastructure, within our organization to be able to do that. Because right now it's just Mark and I, right? We're kind of running with this program. We're going to do it for the 3rd year. We'll do it again in Portsmouth. We chose Portsmouth just because both Mark and I both live in that town, so it was convenient for us to be able to just roll down the hill to the library, right, and be able to do it. But that's what I would ask. That would be my ask if anybody is interested. Do it in your local community, right? Do it with the people in your town. Okay. Oh,
real quick. Did you see any sort of, I guess, crassly stated conversion towards interest in membership for the club here for some of these families? Like, did they start showing up to meetings?
Well, no. Just because, and I think part of that is Rhode Island distance mentality. We live in Portsmouth.
My God.
This is almost an hour away, right? They did actually, some of the families did go because Mark Casey, who's a member here, also is part of, he actually runs the telescope at UMass Dartmouth. Right, which is only 20 minutes away from us. So some of the families did go there because he did mention the open nights that they had there. So some of the families did go there, right, to go look through the telescope there. We did invite them to come here, but we did talk about it. We, gave them all the information. But I think, again, that Rhode Island distance mentality kind of prevented something.
One of the reasons I asked, obviously, is in the interest of the club. But I know in Springfield, when I first got involved in the Springfield Stars Club back in 2019, there were very few young people. And then there was one family, one active family that brought their elementary school kids, maybe some of you know them, Caitlin Gillette, who's now a middle school student, or maybe even early high school, but she started an astronomy club in middle school. So now she's become a point person, and they've leveraged her interest, and she's brought in all kinds of young people to the club.
Oh, that's a great, yeah, that's a great.
Out in newsletters.
Yes.
Yeah, and I thought she was, contributing to our newsletter as well.
Yeah. Yeah, but it took that one
Yeah.
family with the intense interest, they all stargazed together.
That's a great point. I mean, I think that's something we could probably improve is kind of our, putting that out there, right? More information about, about skyscrapers.
I wonder with the older kids too, if you could hook them in some ways with the dark sky initiative sort of approach. Two prongs, astronomy and dark sky, maybe.
Right.
Because they become more conscious and aware of some of these issues
That's true.
when they're older.
Yeah, we have talked about light pollution with them because the location of the library where we are is very light polluted. So we talked about going to darker sites, with them. So no, great points, excellent points. It's good for us to consider those things and like, hey, get away from it. Hey, any other questions, comments? I know I've probably run over my time and I'm the one, I couldn't red card myself. Right? All right.
Yeah, beautiful. So I did a talk about the lunar module back in 2019. It's hard to believe it's already 6 years, like 5.5 years.
Yeah.
Oh, can't hear me? Closer. That better? Is that okay? Can you hear me? I got a pretty loud voice too. Is that good?
Yeah.
Okay. All right. And so I kind of ran out of time. It was a long talk and it was just myself and I love to show this stuff. So this is a lot, there's a lot of things that I've discovered about the Lunar Reconnaissance Orbiter and some of the Apollo missions. And I just learned a lot over the last couple of days. I just threw this together real quick because Mike needed an extra speaker. So I get this on here. All right. So that was a picture of it. That was a CGI picture of a orbiter. Here it is getting packed up, ready to be put into the nose cone. Right. And so solar panels are over here. They're all folded up. That's the high gain antenna. This, I think, is one of the imagers. This is one of the telescopes that they use for like navigation. Pick out stars and it knows where it is in around the moon. So it's all bundled up here, ready to go. And so took off in 2019 and they used it to study topography of the lunar surface, radiation, water ice, and gather data for the new missions coming up, Artemis. It was only intended for a 2-year mission. It's still running now. It's amazing. It will run out of fuel in 2026. Costs $583 million, and it flies at an altitude of 31 miles above the lunar surface. The 3D map of the moon that it produced has a 100-meter resolution. And in 2011, they put it into low orbit so that they could 72,000 feet, 13 miles above the surface, to get good, clear images of the Apollo landing sites. So the map here is focused on Tycho. So this is like the lunar surface is like tilted, like the North Pole would be going to the opposite side. This is like the South Pole right here. So you can see the lines converge. This would be the South Pole right in this area. That's Tycho. Tycho would be right there, that yellow circle. And Tycho is right about there, right above the Mickey Mouse. And you can see the altitude. So there's a chart here for the different measurements that it took. All right, so here are all the sites that are up there. All the Apollos are in yellow, surveyors are in blue, and all the Russian unmanned lunar probes are green. So Apollo 12 landed within 600 feet of Surveyor 3. That is like bullseye. You couldn't get any better than that. So that was a pretty amazing mission for that one. This is kind of a side thing. Nobody really talks about this, but Luna 15 was a probe that they sent up right in when Apollo 11 was making its landing. Luna 15 took off 2 days before Apollo did, or 2 or 3 days, and it crashed 2 hours before Apollo 11. So that's where Luna was 2 hours before Apollo took off right here from this point. So that's pretty wild. A little bit of information that people don't really know about. It's kind of kept secret, and then they let it out after. NASA knew about it. They were worried about it, but once that thing crashed, and it's funny, it crashed in the sea of crisis. Yeah, it had a crisis, all right.
So, John, was the Lunar, that the Russian air?
Yeah, Russia, yeah. So that thing was around, flying around the moon while Apollo was there, you know, and then it crashed 2 hours before Apollo lifted off. Neil Armstrong. So these are like thumbnail images of the 6 sites of Apollo. And I'll go into more detail, but you can see there's the lunar module there, right there. There's another one. There's a lunar module. You even got the rover. It's hard to see the rover in that kind of like dark area, but there's better pictures. You're not going to see it really good, but the resolution on this narrow angle camera is 25 cm, 10 inches. So 1 pixel is equivalent to 10 inches. So just think about the foot pad on the lunar module. It's about maybe 3 feet in diameter. It's like, that's 3 pixels. So it's pretty wild. All right, so they also crashed the 3rd stage into the moon for seismic experiments. The first 2, Apollo 11 and 12, they sent the 3rd stage into a heliocentric orbit. It just went right by the moon and went to the sun. But when Apollo 13 happened and they weren't able to make the landing, they were planning on crashing the 3rd stage into the moon anyway. So it went into the moon. So there's 13, 14, 15, 16's not here, 17 is there, 16 crashed. I have a picture of it, but I don't have it on here. It is available on the internet. And it's about 250 kilometers, I think, south of Copernicus. So they did manage to find it. So that's what it looks like in real life. And this is the 3rd stage here, and there's where the lunar module is nested in there, and the command and service module on top. So there's the 3rd stage, and this was probably pre-lunar, like Apollo, 9 or 10, the test run for it. And the fairings are usually on here. They attach at these points around here and they peel right off. They just blow them off with explosive charges. So this is what happens is as they go to the moon, these command and service module leave this point, turn around, come back, pick it up, pull it out of the 3rd stage. And then all of them keep going to the moon, and then the 3rd stage just goes right into the moon. And it crashed, it takes like 3 days to get there. So here's a kind of a graphic representation of it. These panels would just peel right off. They wouldn't be there because it's sort of a safety hazard. So this is just to give you an idea of what these things look like. All right, so first mission, Apollo 11, June 20th. There's Buzz Aldrin, Neil Armstrong's footprint. Then there's a good view of it. You can see their tracks where they walked and all the experiments here, cameras here, there's the lunar module. And you can clearly see those footprint tracks. In that movie, there was a movie out about Neil Armstrong. It showed him going to the crater and dropping. I think it was like I forgot what it was, a picture or a ribbon or something. I think it was his daughter that just died. Not confirmed, but he dropped it into the crater, so that's the path that he went. Who knows if that really happened? He was very private about it. They put up the lunar laser retroreflector, and there were 3 missions that have this, and they still are in operation today. And McDonald Observatory measures the distance, and the moon is leaving our orbit at a rate of 1.49 inches a year. 3.78 centimeters, 1.49 inches, inch and a half a year. Losing. So Apollo 12, they landed 600 feet from Surveyor 3. There it is. And there's a crater right here. They had to walk around the crater. They didn't want to kind of go down in there, I guess. They plan on going around it. So Pete Conrad, I'm not sure if it was him, but Pete Conrad most likely took this camera off and brought it back to Earth.
Yeah, it was Conrad.
Was it Conrad that took it off? Yeah. So that's
Fought with that thing.
yeah, that's the camera. That's the camera right there. And they use it to study like the effects of micrometeorites and radiation on the equipment. There it is right there. You can see the information up there. Studies of the hardware resistant to damage in severe lunar environment. So this came back off of Surveyor 3, which landed in 67.
Where's that on display?
I'm not sure. It could be like Johnson Space Center. It could be Smithsonian. I don't know where it is. I'd have to look it up. But it's back here. So this is the site for Apollo 12. This image is 275 meters across, 902 feet. So just think of it as 3 football fields across. Okay, so makes sense. These are the walking paths right here. So that's not a long hike. All right, and they might have done a couple of EVAs, just so they might have gone in this direction on one EVA. They've gone in this direction, explored that crater, come around. Here it is here. Well, this is the EVA, the path. They came around. Here's, you can barely see the Surveyor crater. It's a very shallow crater, but you can see the depression. And so the track comes around like this, and then they came over to the Surveyor. They didn't want to go across like that. I think they were just worried about tumbling down in there, or maybe getting using up a lot more oxygen going up the hillsides.
Creating a slide.
Yeah, anything is possible. As a matter of fact, one of the missions with the rover, they actually put it up on a slope, and it tilted up off of one wheel, and it started rolling downhill, and they had to grab it before it ran away. And so that's a true story too. I don't have a picture of it, but I saw it in my research here. Apollo 14, Alan Shepard, his famous golf shot. They got the 2 balls. They were able to see it on here off this picture. And look at the shot one divot, and the second one was obscured by the little rocket engine there, the attitude control nozzle. But they made a special golf club. It was like in little pieces, and he took a couple of shots. And he said it for miles and miles. It went 40 feet. He just was exaggerating. He was like, remember, miles and miles, he said, on the video. So that's a video image of him right there. It's not a really good clear picture, but that's him. That's Alan Shepard. Yeah. And he's the first one that went up in Mercury. He went up and down, didn't go around, but he made it to the moon on the second try. So this is their mission, and this was a walking mission. They didn't have the rover yet. And this is the experiment package over here. And there's this is a narrower field of view because they really want to get in and see that lunar module. So this thing goes way out here. They go to I think it's called Cone Crater, that is further out here. So they took a long walk out there. And then this might have been part of another separate EVA, or it might have been in conjunction with that. But there are 2 paths that go up. So here it is, right? So they're going all the way up here to Cone Crater. And then there's this other one here, which was a return. I'm not sure if this connects to it or if this just went up and back and they followed their tracks back, but this is the path that went all the way up like this, and then they kind of looped back. All right. Apollo 15, Hadley Apennine, and that's in 1971. That's James Irwin. And now they starting to use the rover. Okay. And they got a TV camera on the rover right there. Antenna, talk to mission control, all kinds of stuff that the rover came right out of this compartment right here. So they unloaded it right off of there. It all folds up. It's all like spring loaded. And again, here's where their equipment is. You can see all their paths, walking paths. The rover's parked here. They call it RIP, resting place. Rest in peace. The lunar range retro reflector is right here, and that works today. It's in operation. All they do is just shine a laser beam on it. It comes right back. 100 meter. This I believe is 100 meters. So this band right here. So to give you the scale.
Question, John.
Yeah.
Does that laser reflector degrade whatsoever because of,
Dust? No. Why would it degrade? There's nothing, there's no wind to kick up dust, so there's no degradation. It's just a mirror. It's like a bunch of little mirrors.
John,
Yeah.
from the descent stage,
Huh?
from the rocket, the descent stage.
Oh, no, they put that after they land. Oh, you mean the ascent stage? Yeah. Well, what's the distance? I don't think it kicks out that much dust when it takes off.
You can see
That's 100 feet. That's 300 feet. 300 feet. So it's way out there.
Look at the albedo though, how dark it is compared to the color of the rim itself.
What are you talking about? It's right there. It's a white spot.
Everyone that you see is that like sit wait.
This right here is the rover.
All right. I mean, up there where you put you see that white spot.
Yeah, this one here, passive experiment. There's solar panels on that.
I mean, with each one of them, not just that.
Yeah.
Each one, we could see a very distinct dark circle around the.
Oh yeah, that's probably bloom. It's probably bloom from the chip imaging. You know what I mean? That's why that's.
The footprints.
Yeah.
Yeah.
Well, anyways, we'll move on here. I don't want to. So this is that they did 3 EVAs. Oh, I wanted to go back to this. I don't forget to mention this. This peak, Mount Hadley, 14,000 plus feet. 14,000. I get the number right here.
That's just tall.
14,764 feet. I was just talking to Steve about this. The distances on the moon, and in general, people don't really get the scale of this stuff. Like we were just talking about, go down to Death Valley, and it's what, 2.5 miles across, whatever. Oh, I can make it, no problem. Oh, they don't make it 500 yards. They drop dead because the distance is deceiving. And mountains are, well, you can put your fingers on, oh, mountain's that high, you know? Yeah, it's that big, you know? But that's 14,700 feet up. I couldn't believe it when I researched
Have any
this.
scale there either. No
Yeah,
buildings,
they used the registration marks on this to, get orientation, make sure that it's nice and aligned, horizontal, vertical, and they know the size of the markings so they can judge what's back there using geometry and math.
There's no atmospheric haze, so it looks like it's right behind them.
Yeah.
Yeah.
There is, it's mind-boggling. All right. So this was the 3 trips they made. So that picture was taken. They're standing right there, and that mountain is right up in here. It's right behind them. This is just the beginning, the foothills of that mountain. And this is a Hadley Rill. This is a collapsed lava tube right there. And this is a beautiful shot. This is from that Lunar Reconnaissance orbiter, oblique angle, and there it is. I mean, they were standing here with the mountain right behind there. Off to his left was this Hadley Rill. So they did some trips out here, out over here, all the way up here and back. And this thing would travel 10 to 15 miles an hour too, the rover. It could go at a pretty good clip. like a golf cart, basically. It's a golf cart on the moon. So there it is, all packed up. That's how they can get this thing in there, you know, and it's like, the seats are like lawn chair seats. Everything's so lightweight, so everything's made out of aluminum, and it's just like the seats are just like wicker, you know, there's nothing to it. The wheels are spring loaded. All these ribs here with it's like a cage, it's like wire mesh. There's no tire on it, there's no air in it. You can see right through it right there. You can see the treads right there. They're just metal springs basically with a wire mesh over it. So it's super lightweight. And all of this gold foil, this is just all insulation, super lightweight Mylar with gold, aluminum. It's just a gold color. It's not real gold. It's just a gold tint to it. Be awfully expensive to make that all out of gold, and it would be heavy too. Would add more weight to it. So it's just Mylar and aluminum. They use it for thermal stability, so that things don't overheat in that hot sun. 200 plus degrees, 300 degrees. They took back 840 pounds of rocks over the 6 missions, and they got 2,200 samples, and they broke them up into 110,000 pieces. So this is this number, sample 15415, and they call it the Genesis rock. It's about 4 billion years old. But they got some that are even older. This one really isn't the one that they think that it's part of the lunar crust, but they got one that's a little bit older, but it kind of has a discrepancy in it because they think it might have been a chunk from the Earth that was blasted off and came to the moon 4.5 billion years ago. So it's up for debate on that one. This Descartes Highlands, this is Apollo 16, John Young at the rover. That's a beautiful shot of the lunar module. And this is their site. And you can see there's where the so they have this passive seismic experiment. When those booster rockets crash in, they can this thing picks it up. So the previous mission, so when, like, say for example, when you crash Apollo 15's booster into the moon, Apollo 11, 12, and 14 seismometers are going to pick up that impact. So that's why they crash them into the moon, to study the composition of the moon. So there's the Orion descent stage, and you can really see some detail on that now. I think the orbiter got in a little bit closer. And that's the lunar rover right there. And this is 20 meters. This bar right here is 20 meters. So for the scale. This is Tracy Rock.
I like that.
Tracy's Rock.
Thank you.
Yeah. That is Harrison Schmidt, I think. He was the geologist on this mission. And you usually can tell because they don't have a red stripe on their helmet or on their legs. They put them on after Apollo 12 so that they could differentiate, you know, on the ground, seeing these guys running around, they don't know who's who. So the commander has the red stripes. I think John Young had the red stripes on that last one there. He was the commander. Eugene Cernan. Well, Eugene Cernan, sorry. Yeah, I forgot. Yeah. Eugene Cernan. And the rover's right here.
Smith was the first actually scientifically trained astronaut.
Right.
Correct.
Right. Well, Cernan was on this one with Harrison. I'm talking about John Young. I thought was he the commander?
Of the previous mission.
This was of Apollo.
This is 17.
Yeah, I know. I'm talking about with the red stripes. Yeah, I might have missed it on that image. So this picture shows what the view looked like out the window of the lunar module as they lifted off the lunar surface, and in comparison to the LRO image in 2011, tracks line up. There's a few that you can't see, like this one coming around like that. Well, this one actually is this one right here. sometimes the shadows don't, the angle of the sunlight, if it's hitting straight down or more of an angle from above, you're not gonna see the relief of the shadow of the tracks. And you can see the double tracks because that's from the lunar rover. So single tracks this would be a single track where they were walking, and this double tracks are from the wheels. So you can see them here very well. There's the moon buggy tracks that they call it. It's the rover, and that's its final parking spot over there. And here's all the experiment equipment over there. Astronaut footpath. See that? There's the buggy path, the rover, and these are walking paths. So this is Tycho crater. This is just to show you that they don't just take pictures of the Apollo sites. They take pictures of everything up there. They map the whole surface of the moon. This peak is 6,500 feet plus. That's in the middle of the Tycho crater, and Tycho crater is 3 miles across from rim to rim, approximately. So that is incredible. That on Washington. That is just such a beautiful shot to have that shadow. It really stands out. It's just amazing. Yeah, and then they're mapping water because if they want to send Artemis, they said, well, we're going to need some water if we're going to stay for a little while. So this water has been around for billions of years, and they can use it for a resource. All of this is in shadow on this, shielded from the sunlight. Now, they're showing that this is a neutron count rate, so I'm not sure where this is. It might be under the soil. I'm not really sure, but some of this stuff is in permanent shadow and it's been there for billions of years. So they know that this water is there. It's locked up in ice, and it's maybe beneath the surface, but it's showing up on their instruments. And this final image just gives you an idea of with the shadow angle of the sun angle of the sun casting those long shadows, and you can see this is basically the shadow of the handrails right there. There's those 2 horns right there. That's the handrails on the deck of the lunar module. So, and I think that's it. And then I just got one other thing. We have this. If you want more information about this whole operation of Lunar Reconnaissance Orbiter, they did a PowerPoint presentation back in 2009. This was when they started the mission, and they were doing updates on it. And if I can scroll this. Yeah, so there's what they're planning on doing is the Artemis project. And they're not even sure. I mean, they got Elon Musk supposedly doing his human landing system, HLS. And that contract may just go away. So who knows who's going to pick it up? He may be defunded. We don't know. And he's got a big problem with fuel transfer. Can't transfer on the ground. How are you going to transfer it to space? So I don't know what's going to happen to that. This may be pushed out to 2030 if we're lucky. But that's that Artemis project. Here's mission objectives. So locate resources, safe landing sites, space environment with radiation. They also impacted this booster. They got seismic data off of that. Oh no, what they did was they got a plume of water vapor. They impacted in the South Pole and they got water vapor. So they were able to measure it. Water there. Right, yeah, so they definitely proved that it's there. That was part of the mission. And there's the team. There it is with the solar panels folded up. This is their PowerPoint. This is the trajectory. So you can see how it's mapping. It's just going around and around and around, mapping pole, all of the moon. Detailed into the, you know, all the different specifications. Who's communications. How they doing that, those must be the guidance cameras. There's the, main camera for imaging. Looking down right there, and then these are the guidance cameras, taking pictures of the star so it knows where it's at. So they're doing this, that neutron detector, looking for water vapor. There's another one. Land left, climate alpha mapping, water frost. What's this one here? Cosmic ray detector. Mapping of hydrogen abundance. And it just goes on. Here's another image of how it does the mapping. It acquires the images and pieces them together in mosaic. And they also did communication by laser beam. They beamed an image of the Mona Lisa to the craft and were able to digitize it and send it by laser beam communication. Done. That's it. It's the whole thing. So if you want to read all about this, you can go right on to NASA's website and, you know, download this PDF, or there's a ton of information. That there's a website specifically for the LRO, and it has all these features that you can look at all the pictures that they took to your heart's content. Spend hours and hours on it. So, hey, thanks everybody for being here. I just wanted to follow up on a couple of things that we talked about last time I was here, last meeting. I made a couple of mistakes. I just want to correct them, and then I found some more information that would be nice to share. And this is only going to be like 9 and 10 minutes. So here's Tycho crater. The mistake I made was I said 6,600 feet altitude. It's not 7,900 feet. You got to fact check everything on the internet. There's so many different sources. So that was wrong. The base is 9.3 miles wide. So that's just pretty impressive.
So what is that in kilometers?
Kilometers on it. I mean, I could calculate it. Not in my head though. So I I said that the distance between the rim of the crater, rim to rim, was 3 miles. I was off by 50. So again, that is, yeah. I said to myself, oh, no, that's not right. 3 miles is not right. I got it off of some website and it was wrong. So 53 miles wide. Look at that depth, 2.4 miles. 15,400 feet. That's so unbelievable. Just to think about it, that would be like from Providence to Boston, that crater. Unreal. And it's about 100 million years old. That's what the estimate is, which would be relatively young. And the rays can go out to 1,600 miles. That's just a nice enhanced image of the Tycho crater. It's a beautiful shot. I love the contrast of the colors. Here's a little close-up shot of it. There's Tycho down there. I didn't have a picture of the impact of the third stage, Apollo 16. I found it, and it's 160 miles southwest of Copernicus crater, and it hit at a speed of 5,880 miles per hour. It almost looks cylindrical in the middle. It looks like it could be like sideways to my eye. Maybe I'm imagining it. I don't know, but they definitely know that this was the impact, the debris. Roger had a question about the distance from the lunar module that the reflectors are, and Apollo I found was 60 feet. I had 20 feet for one, 100 feet for another, so it boiled down to 60 feet for Apollo. Apollo 11, Apollo 14, 660 56 feet and then 886 feet for Apollo 15, and they all work today. Apache Point Observatory is using their 3.5 meter telescope. And it's been in operation, doing measurements since 2005, and millimeter accuracy. So then we talked about the rover. I wanted to show you those lawn chairs. All that stuff folds down, all that equipment. And so those lawn chairs are just basically the backs of them folded up. Everything has to be super lightweight. And see what else. So I got some detailed information over here. So the total range of it is 57 miles. They did 15 miles on the EVA. On most EVAs, there was 3 of them on this mission, and then the other 2 rovers, they traveled about 15 miles, I believe. It was designed for a max speed of 8 miles per hour, but Eugene Cernan hit 11.2 miles per hour. That's the top speed. The motors are 1/4 horsepower for each wheel, all-wheel drive, all-wheel steering also. And it uses, believe it or not, the harmonic drive strain wave gears in it. The weight of it on the ground on Earth is 460. On the moon, it's 76. Boeing made it, and they made 3 of them for $38 million. And then they had 1 spare. They also had backup trainers, and then they were also going to build 3 more for the upcoming missions that they canceled. So they got extra spare parts. So here's an example of that strain wave gear. So it has this flexible spline here, goes inside this rigid gear, and then this is an oval right here, the oval bearing. So as it rotates this way, the flexible gear goes 1 tooth that way on a half turn. So you see, this would be right here. It's on the high spot of the wave. Now there's a gap here. See that gap right there? That would be 1/4 of the way around, and this would be the halfway around. So it's 1/2 rotation, and it's moved 1 tooth in this direction. So the elliptical drive wave generator is going this way, but the gear is going that way. And I'll explain it further here. So here's a nice shot of it. There's a little gap right here. Here's where the teeth are engaged up above. This sleeve goes in here. This is rigid. This would be mounted to a housing. And then this is elliptical, this elliptical bearing. So that goes inside there just like that. And there's the contact points. It's about 30% is the teeth are contacted at any point. The gear ratio on this for Apollo is 80-1. So there's 162 teeth on the outer ring here, and there's 160 on the inside. So it basically kind of like skips, doesn't skip, but it has 2 teeth that move because of the less teeth on the internal ring. And it spins, the motor can spin at 10,000 RPM. That's the maximum. So with a 32-inch wheel going at 10,000 RPM, you're going to get 11.91 miles per hour. And he hit 11.2, so that's right in the ballpark. So if you knock this down to 1,000 RPM, you'd have 1.191 miles per hour, just to give you an example how that gearing works. It's an 80-1 ratio. This gear right here looks like it has about 100 teeth, so this would be like a 50-1 ratio. So here's just another example of it. So this is probably a little bit clearer. So you can see that flexible ring is going this direction, and the elliptical wave generator is going in this direction. And this is fixed. And you can see the gap right here. So it's engaged here. Now it's not engaged, but it's engaged on each side here, not engaged here. So it just wobbles. But the hub doesn't wobble. It's just the gear itself. It's a special alloy that they use. And this is what the motor looks like on each of the 4 wheels. It costs $57,000 per motor. Cost of each device. This went for auction for $7,200. Here's the date code on it. Looks like 73, 4th month. Okay. This was probably gonna go on the next rovers that get canceled, so this went up for auction. So looking at this diagram here, here's the motor here. Just take this and flip it around in your mind. See how it's curved like this? It's got the two curves, the smaller curve here. So this rotated 180 degrees this way, okay? And the wheel would be right here. And then here's where your struts are and your suspension connection points are right there. And steering also. All right, now I talked about how this thing was up on two wheels. I didn't have a picture of it, now I found it. So James Irwin got off this thing. This was on Apollo 15, and he forgot to engage the parking brake, and it started getting away on him. And you can see the two wheels are lifted right off the surface of the moon. And this was like about somewhere between an 18 and 20 degree slope, and he kind of grabbed hold of it before it got away on him. Here's a close-up of the control panel. So each astronaut would be one on each side. And so instead of a steering wheel, you're using a T handle. So if you rotate it to the left, it goes left. If you rotate it to the right, it goes right. If you push it forward, it goes forward. If you pull it back, it engages the brake. If you pull it all the way back, it engages the parking brake. And I believe this switch right here is reverse. So you can't just put it into reverse because you jam up the gears. So you'd have to stop it, activate reverse, and then put engage in reverse. And you can see this is like an armrest. So their forearm would rest right on that, right padding, just like your center console of your car. And it's got, this is your, it's for navigation. It gives you the bearings. This is speed, and then there's power and temperature of the batteries. And here it is on the moon, and it's got a traverse map that they were using to navigate. Okay, these are grab handles right here, by the way. Go back, please. So you can see there's a grab handle on each side so they can get themselves in and out of the vehicle. Right. So here they are training on Apollo 16. You can see they've got tires on the ground. So this is working in Earth gravity. You can't have tires in space that pop. But also they're very heavy. If you had solid rubber tires, they'd be really heavy. So everything had to be lightweight. They have a trainer that they would use on 1/6 gravity. See, this would, if you use the real tires that they use on the moon, the wire mesh tires, wouldn't be able to support the weight of 470 pounds. There's two batteries up here, they're 36-volt batteries, so they weigh a lot. And those wire wheels would not support it on Earth. So they made a system of rig so that would be 1/6 gravity with the wire wheels, but they don't just use it for limited training. And then I was talking about the stripes on their suits, so you could designate the commander. So John Young is the commander of this flight and of this mission. And a very cool sun visor, flip up, flip down. It's getting a lunar sample right there, and you can see the camera attached to his chest. That's a nice shot of him. Look at this. Where did the legs go? It's behind a hill that you can't even perceive. This is why I was talking about distances and the way the lunar surface plays tricks on your eyes. It doesn't seem real. It's like, where's the rest of the lunar module? This is a lens flare right here. This right here is passive seismic experiment, a monitor. Where's the lunar module? Like, where's Waldo in this picture? As they've driven away from it, it's easy to get lost, especially, you know, with all the glare and everything. Can anybody find it? You see it? Bottom left. Right there. Look how small. They were probably a mile away from it, you know, or 3/4 of a mile, approximately. I'm just guessing. Just to give you an example of how scale and depth and everything is very tricky on the moon. This, believe it or not, is a Lego model, and shows how the rover is packed up, and then when they open it up, the front and back fold down. This isn't completely deployed, and these are all
activated by springs, so this all of this stuff pops open automatically. So it looks like, oh, well, John, how come the fenders are all the way down here? How's it gonna roll? Well, this hasn't come completely forward. And this one hasn't come completely backward. Then the fenders will be up on top and the wheels will be on the ground. This just shows you how compact it is, and they have to fit it in the descent stage of the Lunar module. So Eugene Cernan driving this on Apollo 17, and you can see the all-wheel steering and all-wheel drive. So these wheels tilt, so they can make a really tight turn. Again, the commander stripe on his right on his helmet right there. You can see a little bit of this thing there. Here's a close-up of the wheel. This is titanium. These treads right here are titanium. There's a titanium frame in here. And this is all steel wire, zinc coated in fiberglass fenders. 32-inch diameter. Let's see, chevron cup, 50% contact there. Titanium bump stop to protect the hub. They broke the fender when they deployed it on Apollo 17. The back end of it, if I go back here, you'll see there's 3 sections. You can just about see it here. See how there's like 1, 2, 3. If I go back here, you can really see it. See how it's broken in sections. It's 3 pieces. So he broke the back end of it off. And what happened was his hammer. He had a hammer in his calf pocket. It's like down below here. It got caught when it got unfolded, and it broke off. So Mission Control said, "No, we'll come up with a fix for you." And they said, "We'll use some extra maps." They're laminated maps. They had some extra ones and used duct tape, and they slapped it on with a couple of clamps. So right here's a clamp here, and they put a clamp on the other side, and it worked. Because as they were riding around, they first did it with just duct tape. It fell off, and it got covered in dust, and things started to overheat, and they were having a big problem. So the hammer stowed in his cap pocket, tap the extension back in place, but due to the dusty surface, they taped it. The tape did not adhere. For the second EVA, the fender was made with some EVA maps, duct tape, and a pair of clamps.
John?
Yep, almost done. And that's it. That's him, Gene Cernan, with dust covered all over him from that episode. And that is it. So if you want more information, if you want to snap these links, you can go onto YouTube. And this one here is on the harmonic drive, which is a really good video, which I have on the computer if you want to look at it later on tonight. And then there's some really good videos on YouTube. And then there's a couple of articles on the Atlantic that are really good, that show a lot of nice NASA photos done.
Thank you, John.
Yep.